Hi. In this video, we're going to continue learning about counting, and in particular, we will learn some formulas for counting permutations and combinations. So let me start by telling you what a permutation is. If X is a set of distinct symbols with cardinality n, then a list of all of the elements in X is what we call a permutation of the set X. So for example, if our set X contains the three elements 1, 2, and 3, 1, 2, 3 is one list of all of the elements of X. So it's one permutation of the set X. How many others are there? Well, there is one other that starts with a 1. So 1, 2, 3 and 1, 3, 2 are the two permutations of X that start with 1. There are also two that start with 2. So 2, 1, 3 and 2, 3, 1. And there are two that start with 3. So 3, 1, 2 and 3, 2, 1. So let's think a little bit about how we would go about counting these without listing them all. Right here we have 1, 2, 3 elements in our set X, and we're going to put them all in a list. So we have 3 choices for which element we list first. After that, we have 2 choices remaining for the second element, and our final element has to be the last element left. So we have 3 times 2 times 1 equals 6 permutations of the set X. So you may have seen the notation of factorials before and recognized that what we had on the last slide was a factorial. So for any natural number n, we define n factorial to be the product n times n minus 1 times n minus 2, etc., down to 2 times 1. And we pronounce that n factorial. We're also going to define 0 factorial to be the number 1. So that's just a definition there that doesn't sort of play with the formula. Okay, so let's look at some examples. So if we have like 3 factorial, that's what we had on the last page. 3 times 2 times 1 is the number 6. 4 factorial is 4 times 3 times 2 times 1. We can also write it as 4 times 3 factorial. And so it's 4 times 6 is 24. Okay. Oh, maybe some other things that would be useful. So for example, often we'll have things like maybe n plus 1 factorial. And it can be convenient to recognize that n plus 1 factorial is n plus 1 times n factorial. I'm going to sneeze. Oh, no. Okay. This is often something that's really helpful in inductive proofs, as you can maybe imagine. All right. So let's see how we can use factorials in an example, say where we're trying to choose a team. So suppose we have 19 students in discrete math, and we want to pick a team of 3 of them to represent our class in some kind of, I don't know, maybe a discrete math contest or something. In how many ways can we do this? Okay, so we have 3 choices to make, and we have 19 students total. So we can choose any one of the 19 for the first spot. We have 18 students left. We can choose any one of the 18 for the second spot on the team. And then for the third spot on the team, we have 17 choices. However, this is a team, right? It's not like there's a first person on the team, a second person on the team, and a third person on the team. The team is unordered. So we have to divide. This is how many lists of three people that I can make from our class, but I have to divide by the number of ways of reordering this list. So I want to say so this is the number of ordered subsets of 3 people chosen from our class. So we've overcounted, right? And we've overcounted by the number of ways of reordering each of these sets. So there are 3 factorial ways of reordering each team. So the number of teams should be 19 times 18 times 17 divided by 3 factorial. So you can see that it's not, once you get used to it, you'll see that it's not too hard to come up with these formulas, but you don't want to write out a big product like 19 times 18 times 17 times ... maybe in the numerator. So what you can notice actually that's kind of cool is that note 19 times 18 times 17 is equal to 19 factorial divided by another factorial, and it's divided by 16 factorial, because if I wrote them out, I'd have something like this, ... times 2 times 1 in the numerator, and then 16, 15, ... times 2 times 1 in the denominator, and all of these would cancel out. So another way of writing this then, I'm going to write it up here, is it's 19 factorial divided by 16 factorial. That just gives me the 19 times 18 times 17, and then I still have to divide by 3 factorial. So you might have seen that formula before, and if you haven't, here it is. So what we did there is we were trying to choose an unordered set of 3 people from our class of 19. So in general, if you have a set of n people, like that's the size of our class, and you want to pick a k element team, so k is so we're picking an unordered subset of k elements, we define n choose k to be n factorial divided by k factorial times n minus k factorial. Okay, so this counts the number of ways of choosing an unordered set of k elements from an n element set. So for example, here's another small example. Suppose that X is the set A, B, C, and D, and I want to look at the number of 2-element subsets of X. Well, the set of all 2-element subsets of X, it's AB, AC, AD. Those are all the sets containing A, and BC and BD. Those are, so now I have all the possible sets, 2-element sets containing B are written down, and then CD. So there are 1, 2, 3, 4, 5, 6 sets. And I can see that by my formula, 4 choose 2 should also count that, which should be 4 factorial over 2 factorial and 4 minus 2 factorial, which is also 2 factorial. This should be 4 times 3 times 2 factorial over 2 factorial times 2 factorial. These cancel out, and I get 12 divided by 2, which is 6. Pretty cool. All right, that's it.